Hello everyone. In this video I'd like to present my solution to a mathematical problem from the Canadian Mathematical Olympiad 2003 problem 2. We wish to find the last three digits of the number 2003 to the power 2002 to the power 2001. And I will give two hints for this problem. It's good to make use of the following two theorems, the Chinese remainder theorem and Euler's theorem. So pause the video if you'd like to try it yourself. Okay, so my solution. First of all, let's call this number A and observe that we want to find A modulo 1000, and by the Chinese remainder theorem it's somewhat equivalent to finding it A modulo 8 and A modulo 125. So let's start with the first part, A modulo 8, because it's simpler. So A modulo 8, let's look here. 2003, it's congruent to 3 modulo 8, and after squaring both sides we will have, on the right hand side we'll have 9, but 9 is congruent to 1 modulo 8. So in fact 2003 to any even power is congruent to 1. In our special case 2003 to the power 2002 to the power 2001 is also congruent to 1 modulo 8, because 2002 to the power 2001 is clearly an even number. So it was pretty easy, I believe. Now the harder part. Harder is finding the second remainder. So by so-called Euler's theorem we know the following fact: because GCD of 2003 and 125 is 1, these two numbers do not have any common factors. By Euler's theorem, we know that 2003 to the power, in fact to the any power k, is congruent to 2003 to the power k modulo phi of 125 modulo 125. Okay, and now again, well, what is phi of 125? By one of many well-known properties of Euler's function, when we have a power of a prime, phi of 5 cubed, it's 5 cubed minus 5 squared. We have power with a lower exponent, so it's 100. So we already know that 2003 to the any power, any integer power k, is congruent to 2003 to the power k modulo 100 modulo 125. In our case, k to consider is 2002 to the power 2001. And let's see, what can we do? So we wish to find, first of all, as a side step, k modulo 100. K modulo 100. Again, by the Chinese remainder theorem, k modulo 100, we'll find k modulo 4, because 100 is 4 times 25. K modulo 4, 2002 to the power 2001 modulo 4, well, it's clearly 0, because 2002 is congruent to 2 modulo 4, and 2 to any power greater than 1 is congruent to 4. In other words, 4 divides this number. Okay? Second step, k modulo 25. K modulo 25. It will be harder. How can we find k modulo 25? Well, again, by Euler's theorem. K to the any power L is congruent to k L modulo phi of 25 modulo 25. What is phi of 25? Phi of 25 is 25 minus 5, 20. So we know that maybe not write k, because k was already used. Let's write any other number. Let's write x here and x here. So 2002 to the power of 2001 is congruent to 2002 to the power 2001 modulo 20. What is 2001 modulo 20? It's just 1. And let's put it maybe over here. And what is 2002? It's congruent to 2 modulo 25. So we established that k modulo 4 is 0 and k modulo 25 is 2. Again, by the Chinese remainder theorem, we know that there is only one number between 0 and 100, such that the following two conditions are satisfied. So which numbers should we check? Let's check the second condition. Which numbers are congruent to 2 modulo 25? Well, 2 itself is congruent to 2, but 2 is not congruent to 4 modulo 4, so no good. Which other number is congruent to 2? 27. 27 is congruent to 2 modulo 25, but again it's not congruent to 0. And the third number is 52, and in fact it is congruent to 0 modulo 4. So after all this, after our reasoning, we've established, in other words, that 2002 to the power 2001 modulo 100 equals 52. 52. Okay. Very well. And what now? Well, now let's go back and recall that we are doing this step. 2003 to any power is 2003 to the power reduced modulo phi of 125. So 2003 to the power 2002 to the power 2001 is congruent to 2003 to the power 52 modulo 125. Okay, so but 52 is still a big number. It's not as big as 2002 to the power 2001, but it's still big. But there is a well-known method to simplify it. First of all, notice that 2003 is congruent to 3 modulo 125. So we wish to find this number. And also notice that 52 in binary system is 32 plus 16 plus 4. So it suffices to find 3 to the 4th power modulo 125, 3 to the power of 16 modulo 125, and 3 to the power of 32 modulo 125. It's pretty straightforward, also it's very boring. I will leave it as a simple exercise. The first number is 81, clearly. The second number after reduction modulo 125, it will be 96, and the third number will be 91. So 3 to the power 52 is congruent to 81 times 96 times 91 modulo 125, and again it's easy to simplify but boring to get that this product is congruent to 116 modulo 125. Amazing in some way. So we have established that 2003 to the power 2002 to the power 2001 is congruent to 1 modulo 8. It's congruent to 1 modulo 8, and also the same number is congruent to 116 modulo 125. Again, we have to make use of the Chinese remainder theorem to find the unique number between 0 and 1000 such that the both of the following congruences are satisfied. Well, so let's look. Which numbers are congruent to 116 modulo 125? So 116 itself, but 116 is not congruent to 1 modulo 8. The next number is 116 plus 122, 431. Is 431 congruent to 1 modulo 8? Yes, it is. Yes, it is. So, in fact, we have our answer. 2003 to the power 2002 to the power 2001 modulo 1000 is just 241, and it's our answer. The last 3 digits of this big number is 241. Thank you for watching.